Yes.
Yes, sir, we can hear you.
Okay, good, good. So last time what we are doing in, does anyone remember? So what are you what we are doing last class? Huh? Yes. Does anyone remember what we are doing in the last class? Yes.
The multivariable power series, and
Power says yes. So why we are doing that?
because like we want to solve PDE, like we
Mm-hmm.
assume our solution will be of the form power series, and then we
Okay,
try to
okay,
solve.
good, good. So we are trying to solve some PDE. We are seeking some power series type solutions, okay, for some particular kind of PDE. And we will study whether the solutions are unique or there are non-power series example of the PDE which also admits non-power series solutions and all those things, okay. For that reason, we are studying multinomial power series. Why we are studying a multinomial power series? Since we will be dealing with the partial differential equation, not the ordinary differential equation. So the ordinary differential equation, that single variable power series is enough. That the concept of real analytic functions and all those things. That now we want to generalize this concept to multiple power series. That means that alpha will come into play. Alpha is the multi-index, as you so know, because in the PDE is the equation involving partial derivatives, and that partial derivatives and all those things can be given. It can be expressed through multi-index, and because of that reason, we are studying some multinomial, or you can say multiple power series with that the alpha runs over the multi-index. Okay, so just recall is that, so just recall the definition. Can you see the whiteboard? Yes. Hello, can you see?
Yes, sir.
Okay, okay, good, good. Let omega is a subset of Rn, be open, and f is a function omega to R. Then f is said to be real analytic at x naught belongs to omega if we can write fx summation alpha a alpha x minus x naught to the power alpha for all x in some open set containing x naught. Okay, and in that case we know a alpha is given by d alpha at f of x naught by alpha factorial. Okay, and we know that alpha is a multi-index. That means alpha 1, alpha 2, up to alpha n, and alpha i's are in the natural number union 0. These are the multi-index. And what is the meaning of x to the power alpha? When x is in Rn, this is nothing but x1 alpha 1, x2 alpha 2, xn alpha n. Okay, so this is the meaning notation. So x minus x naught is an obvious notation, and a alpha the coefficient for each alpha is for each multi-index alpha, a alpha is belongs to R, and this is okay. So we say that f is real analytic at the point x naught. This is, let's say, x naught. This is your omega. This is your x naught. If you can write fx in, there exists an open neighborhood around x naught, so that you can express fx in terms of the power series, this multinomial power series. Then we call f is real analytic at x naught. Okay, then we call a very important lemma. We did a very important lemma, this one. Let omega be a connected open set in R. Open set in R. And f comma g are the real analytic function, b2 real analytic function. Okay, in omega. Suppose for some x naught. In omega, we have d alpha at x naught is equal to d alpha of gx naught for all alpha. Then what will happen? Then what will happen then?
F will be equal to G.
F equal to G where?
Omega.
Huh? F equal to G where?
On omega.
On full omega, right? Then F equal to G in omega. Okay, we did this proof. Okay, then what we did is the following. Then we stopped at the some point, right? Remember that lemma where we stopped? Can you tell me the lemma? We did not prove the whole lemma, right? You remember that lemma? Can anyone tell me the statement? What happened? Can anyone tell me the statement? Can anyone still tell me the statement where we stopped? What is that lemma? Next lemma we did.
Like say if we have a power series which converges for some x, like power series of the form summation a alpha x minus x naught raised of alpha, where alpha is a multi-index. So that converges for some x. So then, so if I take
for
any
some x
small,
where? For some x where?
like some x, like kind of in omega, like in a kind of Rn.
Okay, let me write down again. X with xi minus x naught belongs to R. Okay, then the power series converges uniformly in this set. Okay, that means this says that suppose you have some ball or something, it's not a ball, somewhere at xi, then if you have a ball, then the power series converges inside also. Okay, is the statement clear? So we proved this part, right? And there was another part, and the function fx is summation alpha a alpha x minus x naught to the power alpha is c infinity in x such that xi minus x naught I less than r. Okay, the proof, we did the proof, right? What we proved, you remember? So anyone remember what up until which part we completed the proof? If you don't say anything, then I will not do the proof.
So we have shown that this power series converges uniformly on this set x such that xi minus x naught I is less than equal to ri.
Converges uniformly. Yes. Next, what we have to show? The first part is done. So the next part is
F is C infinity.
F is C infinity. The function f is summation a alpha x minus x naught to the power alpha is C infinity in that ray, in that interval. So for that, what we have to show? That also we have discussed. For to prove this function is C infinity, what we need to show?
That summation a alpha d beta x minus x naught raised to power alpha converges uniformly in this domain.
Did you understand why, Ankit?
No sir, that is not clear sir.
That is not. So this is the way you should ask me. Is that this? Otherwise, I don't understand. Are you really able to understand or not? Whenever I ask something, you keep. If no one answers, what is this? Yes. So for these, we have to show that the function, this is C infinity. That means, what is the function? Fx summation alpha a alpha x minus x naught to the power alpha. To show the function is C infinity, what does it? What we have to show? We have to show for any d beta, for any beta, for any beta in the multi-index, index d alpha beta exists. Yes or no? Yes or no?
Yes sir.
For any beta one, whatever the power, for any beta dfx, this imply, then this will imply f is C infinity. Okay. Clear? Yes or no?
Yes sir.
Okay. Now, what does it mean d beta of fx exists? Means this series, if you just formally derive the series, d beta of f, just formally, I am not doing the exact way. When I could write this series alpha equal to d beta x minus x naught. When I could write this? When this is equal to this? When? Tell me. When I can write d beta of
When
fx
the
equal
right
to
hand side series converges uniformly so that we can interchange
exact,
summation and
exactly. This I can write d beta of fx equal to summation d beta over if and only if this series, this right hand side series converges uniformly. Converges uniformly. Then I could write d beta this, and this means these imply d beta fx exists. Understand? So for this reason, that means d beta is C infinity. This implied. That means we have to show these. First of all, we have to start with this series, and we have to show that this series converges uniform, and then we could write this. Is this clear? Is this clear? All of you?
Yes sir.
Okay. Okay. Good. Now let us start. So that is the reason we will be doing now to prove f is in C infinity. Now to prove f is C infinity, we show that summation a alpha d beta x minus x naught to the power alpha converges uniformly. In x such that xi minus, you have to be very careful here. R is strictly Ri, or R is Ri, R is strictly Ri, let's say Okay, clear? So that is why if you see the statement, I have not included capital Ri for strictly less than Ri. Okay. Okay. For any beta. For any beta. Fix 0 less than Ri, some Ri. For I equal to 1, 2, dot, 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 dot. We want to show summation alpha greater than beta a alpha, alpha factorial, alpha minus beta factorial, x minus x naught to the power alpha minus beta is convergent. Why is this true? Huh? Why? To show this, it is enough to show this. Why? Hmm? Why? Huh?
Because we
Why?
know that the beta of x minus x naught raised to alpha is nothing but this expression.
Exactly, exactly. We have done this. Alpha minus beta factorial, x minus x naught to the power alpha minus beta. Okay? Okay, good. That means we need to show that for alpha greater than equal to beta. We have done these examples. We have to show that this is convergent. Okay. But now we have how to show that? Let's see. Since what is given? It is given that summation a alpha x minus x naught to the power alpha is convergent for x, for some x such that at the boundary less than Ri. Okay, these imply summation a alpha x minus x naught, this is r1 to the power alpha 1 dot 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 rn to the power alpha n is finite. Agreed or not? We have given in the hypothesis that a alpha summation a alpha x naught minus x naught to the power is convergent for some x such that this is at the boundary. That means when x minus x, what is this? What is x minus x naught to the power alpha? This is x1 minus x naught 1 to the power alpha 1, x2 minus x naught 2 to the power alpha 2 dot 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 xn minus x naught n to the power alpha, and x9 minus this is because for x is in Ri, so this is r1 to the power alpha 1, r2 to the power alpha 2 dot 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 rn to the power, and summation is because this is the definition of the convergent. Okay, these imply there exists a constant, positive constant c such that mod a alpha r1 to the power alpha 1 dot 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 rn to the power alpha n is less than c. Why? Who will tell me why? I said that this series convergent. Okay, for all alpha. These imply there exists a constancy such that this term is less for every n. This is less than c. There exists a c such that this happens. Why? Who will tell me? No? Why? Why?
So like this series converges with nth term must be convergent and hence bounded.
Think properly. Summation xn is finite. What does it mean? Huh? What does it mean? What does it mean? Xn is a just sequence. You take your favorite, not the multinomial. Summation xn is finite. What does it mean? This imply? Huh? What does it mean? This imply limit xn tends to
0.
huh? 0 imply. Clear for all. Clear? Is that clear? Yes, sir. Yes or no?
Yes.
So this I have used. So this imply the same trick here I have used. C by r1 to the power alpha 1 dot dot dot. Of course, r is a positive number. Rn to the power alpha n. This is, let's say this is, I will use somewhere this part. Okay. Now consider this summation. Alpha greater than beta. A alpha, alpha factorial by alpha minus beta factorial x minus x naught to the power alpha minus beta, which is less than equal to summation alpha greater than beta summation a alpha, alpha factorial by alpha minus beta factorial x minus x naught to the power alpha minus beta, which is equal, which is less than equal. What is a alpha? You use this product. A alpha is less than this. Okay, a alpha is less than this. C by r1 to the power alpha 1 dot 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 rn to the power alpha n summation alpha greater than equal to beta alpha factorial by alpha minus beta factorial. So and mod of x minus x to the power alpha minus beta. And this is less than equal to, you know that we want to prove the convergent when x minus x naught, you know what is that meaning. We want to prove x minus x naught I xi minus x naught I less than ri. You remember? We want to prove here. So if I do this, which is be less than equal to c by r1 to the power alpha 1 dot 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 rn to the power alpha n summation alpha greater than equal to beta alpha factorial alpha minus beta factorial into r1 to the power alpha 1 minus beta 1 dot 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 rn to the power alpha n minus beta n. Clear? Agreed? All of you agreed? So here I put it like this. So agreed or not? Huh?
Yes.
Okay. These I write some small trick. I can write small into r1 to the power beta 1 dot 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 rn to the power beta n. Okay. This alpha I put it inside. Okay. And I will be getting so I have to beta minus alpha. So this is summation alpha greater than beta alpha factorial alpha minus beta factorial r1 by capital R1 alpha 1 minus beta 1 dot 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 rn by capital Rn alpha n minus beta n. Yes or no? Alpha is there. I multiply with inside r1 to the power beta 1 dot 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 rn to the power beta n and divide by r1 to the power beta 1 dot 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 rn to the power beta n. Then r1 by this I make it r1 to the power alpha minus alpha 1 minus beta 1. And this is that clear? From this step to this step is clear? Yes or no?
Yes, sir.
Okay. Now can you tell me this series is convergent or not? Huh? We did this.
Yes, sir.
Summation x to the power alpha when mod xi less than 1. So r1 by capital R1. So you just see what I have taken r1. So ri by capital Ri is strictly less than 1. That is why strictness is important. Okay, the strictness is important. So this is convergent. So each this is strictly less than 1. So we obtain c by r1 to the power beta 1 dot 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 rn to the power beta n summation alpha greater than beta alpha factorial by alpha minus beta factorial r1 by r1 dot 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 rn by capital Rn alpha minus beta. Each term is less than, strictly less than 1. And this is finite. And these imply summation a alpha d beta x minus x naught to the power alpha converges, but you have to be careful, uniformly on xi minus x naught I less than equal to Ri, which is strictly less than Ri. And this implies d beta fx exists for all x such that xi minus x naught I is less than Ri. This implies if is C infinity in this domain. Clear? The proof is clear? The proof is clear?
Oh, yes, sir.
Okay, good. So I wait for 2-3 minutes. If you have some question, you can ask me. Otherwise, I will move to the next theorem. This is a very important next theorem I will be proving. Very, very important theorem I will be proving. Is that clear? May I go to the next theorem?
Yes, sir.
Okay, thank you. Next theorem, something, this is, I don't know whether you have studied in the first real analysis course or not, that this of course works for the simple power series also. This is a necessary, and we have seen that if the function is real analytic, then obviously it is a C infinity, right? Now the converse is not true, you know. If the function is C infinity, there is a function which are C infinity which are not real analytic. Yes or no? Huh?
Yes, sir.
Yes, sir.
Now this will give a necessary and sufficient condition. I don't know whether you have studied in this. It's a very, very important theorem, and it's a beautiful theorem. Let's see. Let omega be a open subset in R in open. Okay, and f is C infinity of omega. Then f is real analytic. It's a characterization. It's a beautiful characterization in omega, if and only if for every compact set K, set K contained in omega, there exists M positive and R positive such that d alpha fx mod alpha for all x belongs to the complex set for all alpha. This theorem says that. So earlier we have, just before the last lemma, what we have proved, if the function is reanalytic, we know it's a C infinity functions, and the converse is not true. Now, these will give you a necessary and sufficient condition. Let omega be open and f is a C infinity function. Then f is real analytic in omega if and only if for every compact set K contained in omega there exists a M positive and a R positive such that now modulus of d alpha fx is less than m mod alpha factorial r to the power minus alpha. This should work for every x in the compact set and for all multi-index alpha. Is that clear? The statement is clear. Just see the statement. Let omega be an open and f is C infinity, then f is real analytic in omega if and only if for every compact set K contained in omega there exists an M and R such that this holds. Is the statement clear to all of you? Yes or no?
Yes, sir.
Okay. So first, which part I will prove? Suppose f is real analytic. F is real analytic. Okay, so we have to show that Suppose f is real analytic, then f is real if and only. So we have assumed that f is real analytic. Then what we have to show? Then we have to show that for every compact set K contained in omega, there exists an M and R positive such that this one. So we have to show that for every real analytic function, for every real analytic function, and for every compact set, and then if f is a real analytic function, then for every compact set, this condition holds true. Okay. Okay. Let me show you how it works. Okay. Fix some point. Fix x naught belongs to omega. Since f is real analytic at x naught, this imply there exists R positive such that fx is summation d alpha of fx by alpha factorial x minus x naught. X naught, the x naught, f is real analytic x naught, so this happens. For all x, we can write around x naught, fx can be written in this way. These imply as before, these imply there exists a C positive such that this as before, such that the n at this series convergent, that means, and what is the distance between x minus x naught is R for every I. So R to the power mod alpha. So these imply d alpha f of x naught, sorry, this is x naught, sorry, because real analytic at x naught, f of x naught by alpha factorial x minus x naught equal to R. So I can take R1 here, R1 is R, R2 is R. So R to the power alpha 1 plus alpha 2 plus is mod alpha. Yes or no? This is clear. Why R to the power mod alpha? Huh? Yes or no? Because this x minus x naught I can write x I minus x naught I to the power alpha 1, x naught 2 minus x2 minus x naught 2 to the power alpha 2 dot 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 xn minus x naught n to the power alpha n. But we know that x minus x naught all are less than equal to, so it is real analytic at the point R also. The series convergent at R. So x minus xi minus x naught I is R. So R to the power mod alpha. Is that clear? Yes or no? Where mod alpha is alpha 1 plus alpha 2 plus dot 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 alpha n. Okay. There exists a C such that infinity. Okay. Now d beta f of x. What is this? We already know this, right? Alpha greater than beta d alpha f at x naught by alpha factorial. Sorry, yes, alpha minus beta factorial x minus x naught to the power alpha minus beta. This we already know. Now what is modulus of d beta? Because we have to show this, right? D beta of fx is less than summation alpha greater than equal to beta dr. This goes cancel f of x naught 1 by alpha minus beta factorial x minus x naught to the power alpha minus beta. The modulus. Okay. Okay. What is sorry. Mod is there here. Okay. So what is d alpha of f at x naught? D alpha of fx x naught is, what is modulus of d alpha at f of x naught? Is less than c alpha factorial r to the power mod alpha. To substitute this for alpha, this is equal to c, a constant. This constant will depend obviously on x naught, because for x naught I have found this. This should depend on x naught. Yes, because d alpha of x naught r to the power alpha is less than c at x naught. Because if I change, if it's dynamic at x different x1, then we have a constant which depend on x1. We know that this. Okay, so c at x naught summation alpha greater than equal to beta, and this comes alpha factorial. You can write this alpha factorial because this alpha factorial comes from here by d alpha fx naught. I am just plugging it this amount, this quantity. Alpha factorial alpha minus beta factorial r to the power mod alpha x minus x naught to the power alpha minus beta. Just I substitute this this is less than equal to this quantity. That's it. Okay. Now suppose xi minus x naught I is less than equal to r by 2. Then d beta f of x is less than c x naught. So we have now this quantity, right? This is there, right? This is there. So I have just used this estimate less than c alpha factorial. C always depend on x naught, alpha factorial into r to the power minus mod alpha. I substitute this part here, but still this part is there, right? C x naught summation alpha greater than equal to beta alpha factorial by alpha minus beta factorial. So here also we got x naught minus less than r by 2. So what I will get from here? Can anyone tell me? What I will get from here? What I will get from here? Less than equal to? What I will get from here? Huh?
R raised to the power minus mod beta.
R by 2, man. This is r by 2 to the power mod alpha minus beta. So this into r by 2 mod of alpha minus beta into r to the power mod alpha. Clear? So this is equal to nothing but cx naught alpha minus beta alpha factorial by alpha minus beta. What I can write this? R to the power mod alpha minus beta into r to the power mod alpha into 1 by 2 to the power mod alpha minus beta. What I can write this? Who will tell me? Just think. Mod alpha minus beta minus mod alpha. What can I write? Equal to r to the power? Huh? What
Minus
I can
mod
write?
beta.
Yes, very good. R to the power minus mod beta. Because this is alpha 1, you know, this mod is not that mod. This mod is just a what is mod alpha is, let's say alpha 1 plus alpha 1 comma alpha 2 dot alpha n. So mod alpha is nothing but alpha 1 plus alpha 2 plus just a coordinate wise summation. So this is immediately equal to r to the power mod. You can check with any alpha beta. Okay, this is equal to r to the power mod beta. So this is cx naught r to the power mod beta summation alpha greater than equal to beta alpha factorial alpha minus beta factorial, and then I get half mod alpha minus beta. Okay, so is that series convergent? Remember? Remember when x is convergent, when xi is less than half. Here your xi is equal to, sorry, xi is less than equal to 1, strictly less than 1. And here all your xi is what? All your xi is, what is your x in this case?
Half.
Yes, x is nothing but half dot n times half. Okay, and we know that this series is convergent, and you can also express in the sum cx naught r to the power minus beta, the sum is beta factorial by, you remember, 1 minus 2, which just check, we have written this summation. Okay, the value of this summation. Okay, this we write, and this means we got this is equal to cx naught 2 to the power n. Okay, this and beta factorial 2r to the power minus mod beta. So this, if you just plug in 2 comes 2 to the power n, 2 above goes to the power n, and you got this. Clear? We got this. Okay, these imply there exists an open set containing x naught and m which depends on x naught and r at x naught all depend on x naught. These r also depend on x naught, such that we got d beta if. So each point is less than, this is your, let's say, m at x naught, m which depends on x naught, this is your beta factorial, and this is your rx naught to the power minus mod beta. So each you have obtained a point wise, but the theorem says that you have to prove this is for all compact set. What you have to do now? So for each point we obtain this estimate. Now for a compact set, what I have to do? We obtain an estimate for each point. Now we have to show that these estimates hold independent of the compact set. We have to show that these estimates hold for any compact set K. Of course, that constant depend on that M and R. That constant depend on the choice of a compact set. So what we have to do now? Let
just
K be a compact set. Just use the definition of compact set. Compact set. Then K can be covered by finitely many open sets. Sorry, this is fx. This holds for every, this for every x in the, you can say for all x such that xi minus x naught I is less than r. For this type of, so this is x naught. So a set of, so this estimate holds for every point x naught around the open neighborhood containing the point x naught. This estimate. So d beta of fx. So we start d beta of fx. So d beta of fx is less than this, but it's of course depend on the reference point x naught. Okay, now we have said that K is a compact set. Then K can be covered by a finitely many open set for which the above estimates, the above estimate holds with constant. So you have, let's say this is your compact set. So you have x1, you have this open set where this estimate holds. x2, you have this estimate where this estimate holds. x3, x4, x5, x6, like this. There are finitely many xi. We cover the x1, x2, x3, x4, let's say x5. So this, for each x size, the estimate holds. Okay, with constants m of xi and r of xi. Now you take m to be maximum of xi and r to be minimum of this r of xi. Okay, then we get d beta fx is less than m beta factorial on the compact set for all beta. Clear? Is it clear? Is this clear? Is that clear? Is the proof clear?
yes, sir.
All of you? For all of you, it is clear? Is the proof clear to all of you? Ankit, Shammi, Ekant, Sanjeev, Yash, huh? Nirmal.
Yes, sir.
Okay. Now the converse part. So we have to show that if this estimate holds for any compact set K, then we have to show that the function is real analytic. Yes or no? Now we have to prove the converse. Okay. This is very interesting proof. Okay. Not difficult. Can anyone have any idea how to do this? Now the converse.
Like we know the coefficients of series are nothing but d beta
No.
x b factorial.
We have to prove and that series converges, right? We have to show that series converges, and we can write f to be like that. So for that, what we have to do? Suppose f c infinity and satisfies the given hypothesis. So what we have to do? How to start with? To prove something f is analytic. That means you can write f as a power series. So what we have to do first? This we have studied. You have studied in real analysis. Just think, when you could write the function as a power series. When? What you have to check? Just think about the real analysis case. Don't worry about the multi-index, all those. I am saying that you could write the sin x as Good.
It should converge first. The power series
should converge. No. First, my question is, when you could write a function in terms of a power series? When?
If it is infinite times differentiable.
So any infinitely differentiable function is you can write a power series e to the power minus 1 by x square, as I was proving that if f is a c infinity function, then if there are functions which is not, we cannot write it as a power series like e to the power minus 1 by x type of function. The converse is not true, right? We have proved that. Every c infinity functions are not power series. You are not real analytic, right? So just I am asking the beginning. You remember, if the function is c infinity or something, what you can write about the function? Or suppose the function is n time differentiable. At least what we could write? Which series you can write?
Taylor expansion.
Exactly. You can write the Taylor's expansion with some remainder term, right? For any nth term, nth differentiable function, you can write a Taylor series, but with some. What is the Taylor series? What is the Taylor series? If the function is, if f is n time differentiable, and smooth all this, C1 and all those things, then you can write fx in terms of f of x naught plus blah blah blah, but up to fn factorial at the point x naught by n factorial into some remainder term, right or not? X minus some xi to the power n plus 1 or something like that. So the problem is with the remainder term. So we can write the infinite Taylor series if this remainder term goes to
0
as n tends to infinity. Then we can say that this has an infinite power series. Yes or no? The finite Taylor series, Taylor's theorem, we can always apply for n time differentiable function, right? But then there will be a huge remainder. You don't know what is the estimate on that remainder term. So you can write, this is the way you write a sin x. You not directly write how you know that the sin x has a power series expansion. You write sin x, first you write the sin x in the Taylor's theorem. That gives you n time differentiable, and the Rn and the plus Rn, you remember the remainder term. This is your Rn remainder term. But we say that since it is C infinity and the Rn goes to 0 as n tends to infinity. As Rn tends to 0, as n tends to infinity, we can write then we say that, okay, it has a power series expansion. That is the way we say, right? Yes or no?
Yes, sir.
It seems that you don't remember. Anyway, so this is the strategy we will adopt here also. Okay? The same strategy we'll adopt here also. So we want to show that F is real analytic. Okay, let x naught belongs to omega. So we have to show that f is real analytic at every point. Okay, let us choose an arbitrary point x naught in omega. Okay, choose R positive such that this compact set, you define a compact set such that xi minus x naught I is less than R. Okay, is contained in omega, is contained in. So you have an x naught. So this is the scenario. So you say, let's say omega, this is your omega. You take any point x naught. Find a ball around x naught with this x, with that. Find there, then there choose an R, choose R positive. This R you have to choose positive. Choose R positive such that xi minus x naught I is less than equal to R. This set is contained in omega. You know what is the meaning of that. Okay. Then of course clearly this set K is a compact set. It's compact. Therefore we know that. Therefore there exists a M positive, R positive corresponding to this set. Corresponding to this compact set. This compact corresponding to this compact set such that there holds the hypothesis d alpha f of x is less than, what is that, alpha factorial. I don't remember what is that, alpha factorial. What is that, alpha factorial into m into alpha factorial r to the power mod alpha. This holds true. Okay, so I choose any point x naught. You take an open neighborhood around x naught such that this open neighborhood not open neighborhood, open and close, this less than equal to r, open and closed neighborhood around x naught. We choose that r such that this is contained in omega. Then K is a compact set. So this is your compact set and it is contained in omega. So corresponding to this compact set K, what we have chosen for that R, there exists an M and R positive corresponding to this compact set K such that this holds. Clear? Is that clear? Yes. Now you take, okay. Now you choose. So there are this R. This you have chosen this R so that this compact set is contained in omega. And you have this R. Where is this R coming? This R comes from the that hypothesis. For every compact set, there is a M and R. So there are two R, this R and this small r. So you choose R1 positive such that 0 less than R1 less than minimum of this capital R you have chosen, and this R we are getting from this compact set. Okay. So I have taken R1 is less than minimum of capital and small r. Is that clear? How I have chosen this R1? Yes or no? Please tell me yes or no.
Yes, sir.
Okay. Now the claim. Claim is the following. We can write fx. We can write fx as this. For any alpha, d alpha f of x naught by alpha factorial x minus x naught to the power alpha for all x such that for those x which is less than equal to r1. Okay? Okay. Proof of claim. So we can write, we will be writing around this R1, chosen R1, we will be able to write fx as a power series expansion. So this proves that f is real analytic at the point x naught. Since x naught is arbitrary, we should prove that f is real analytic for any omega. Is that clear? Is that clear? How I will be showing f is real analytic in omega. Is that clear?
Yes, sir.
Yes, sir.
Okay, good. Proof of the claim. Let x belongs to omega such that x lies in this set, sits inside this set. Okay. Now you define it. So the main idea is I have to write down the power series, Taylor's expansion. So you write down one variable function. It's not plus t. This type of tricks you have been using in the Rn calculus. Define gt in terms of just as a function of one variable, x plus t, x minus x. You just write down the gt as the parameter t so that you are in the line segment joining the point x and x naught. So this along this line. So this is your x naught. You take some x here. This is your x. So you write down any x inside in terms of this in this way. This is a very standard trick. Okay, so g is now a one variable function because x I have taken a fixed x in omega and x naught is always fixed around that where we have to show that. So gt is this. So gt is a one variable function, and we know that f is c infinity function. This imply g is also c infinity of r now because this is a one variable. So I make this is a very important trick. I make the function f like this as a one variable function using a parameter t. Okay, this is very useful. G is C infinity R. So I can write Taylor's theorem. Now apply Taylor's theorem. Taylor's theorem on G. Just note that what is G of 1? What is G of 1? What is G of 1? What is G of 1?
Fx.
Fx.
Very good. What is G of 0?
Fx naught.
So I will write the Taylor series G1 and G0. Okay. So then what is fx? Fx is equal to g of 1. So you write 1 in terms equal to g0 plus g prime 0 plus dot 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 1 and 0. You know x 1 that factorial is 1. So g nth derivative at 0 by n factorial plus the remainder term I will write. I will use the integral remainder term in the Taylor series. Okay. 1 minus t to the power n 1 by n factorial unto the power g n plus 1 derivative at the point t dt. Everyone familiar with this remainder term? There are three types of remainder term. You remember, no? You just go and check. One is the integral form of a remainder term. You know what is the f prime of xi by n factorial, that type of remainder term. You know all these things, right? Yes or no? You know all those things?
Yes, sir.
So this is known as, so if you don't know, you just click in the web, in the Google and then check in the Wikipedia. This is called the integral remainder term. Okay. So this is the form. Now what? Now can you see what is? Can you tell me what is g prime of 0? What is g prime of 0? Huh? What is g prime at 0?
Fx naught into x minus x
Huh?
naught.
What is?
F
Huh?
prime x naught into x minus x naught.
Very good. Now I am saying that what is the meaning of f prime of? You forget, this is a two, this is a, what is this? This is a composition of two function. F of u, let's say u of t where u of t is x plus tx naught. You have to use the chain rule, f prime. So if g prime of t is f prime into u prime of t. Yes or no? What happened, man?
Yes, sir.
So what is u prime of t?
So that will be x
U
minus
prime
x
of t
naught.
is x minus x naught. Yes. And what is this? F prime of ut is the all possible derivative. It might have dlf by del x1 into x minus x naught, or it might have del x by del x2 into x minus x2. Yes or no? Yes or no? Forget all these things. Sorry, del f by del x1 x into x1, del f by del x2. You don't remember these things? You don't remember chain rule? Shammi, Ankit, Yash, Shivani, Annu, you don't remember the chain rule?
Yes, sir, we remember.
Then why you said just f prime of x plus? So where will be this? And what is f prime? It is a del f by del x1 plus del f. Remember, right? Plus del f by del x2 into u prime t del f by. Yes or no?
Yes, sir.
Yes, sir.
Okay. So if you write down, so this will be right. If you check, if you wish, you can check. Please check. Mod alpha, all the multi-index will be covered. D alpha of f of x naught by alpha factorial x minus x naught to the power alpha plus 1 by n factorial 0 to 1 minus t to the power n. If you take g prime, it will be summation mod alpha equal to n plus 1 mod alpha factorial by alpha factorial d alpha f of x naught dot 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 into x minus x naught to the power alpha. Please check with multi-index alpha 1 and 2 or 2 0 1 1 like this. Please check this. Why I am writing this? Please check this. So just again I am writing mod alpha is less than equal to n d alpha f of x naught by alpha factorial x minus x naught to the power alpha plus 1 by n factorial 0 to 1 minus t to the power n summation mod alpha equal to n plus 1 mod alpha factorial by alpha factorial d alpha f of yes plus t of x minus x naught into x minus x naught to the power alpha. Okay, now we have to show that this term goes to 0 as then we can write that summation for all mod alpha for any alpha you put. So we have to show that this remainder term goes to 0. This is the remainder term. Then it has a power 6. Okay, clear? Now for that we have to see that 1 by n factorial 0 to 1 minus t to the power n summation mod alpha equal to n plus 1 mod alpha factorial by alpha factorial d alpha f of x naught plus t x minus x naught dot x minus x naught to the power alpha. This modulus I have to show goes to 0. This is less than equal to modulus. As the modulus goes, summation, this is a finite summation, can come out of the integral 0 to 1 minus t to the power n mod alpha factorial by alpha factorial. You take the derivative of this. What I have to use here? Somehow I have to use the this property, right? D alpha of fx is less than m alpha factorial r to the power mod alpha. Somehow I have to use this fact, right? So where I have to use? once the where I have to use. Where I have to use.
So in the above expression, d alpha of f of
Mod of d alpha f x naught plus t of x minus x naught. If I use it, because this is sitting inside the compact set, this point is inside the compact set, yes or no? X naught plus t of x naught is t of x minus, this is sitting inside the compact set. If I use this m into less than, this will be mod which is less than alpha factorial m r to the power mod alpha. Okay, alpha factorial r to the power mod alpha, and this x minus x naught again you can write r1. We know why I am writing. Okay, so this, if I write down this is nothing but m into k factorial mod alpha equal to, sorry, n factorial n plus 1. So sorry, all these are alpha, is all right. Okay, so okay, this is the thing. So mod alpha factorial, and I will be getting r1 by r mod alpha. This r1, this will be clubbed. This is r1 by r mod alpha. This comes out. This alpha times alpha gets cancelled. Mod alpha, this comes out. So the, and this, and the integration 0 to 1 1 minus t dt stay here. 0 to 1 1 minus t to the power n dt. Okay, if I do the integration, it will be m into n factorial into n plus 1, because if I do n plus 1 by n plus 1 and 0 to 1, it is 1. So summation mod alpha equal to n plus 1 mod alpha factorial. Okay, mod alpha factorial, and this I will be getting r1 by r to the power mod alpha. Okay, so this is nothing but by n plus 1 factorial. Okay, n plus, this is mod alpha equal to n plus 1 mod alpha factorial, mod alpha factorial r1 by r to the power mod alpha. So what happened? And mod alpha equal to n plus 1, right? Mod alpha equal to n plus 1. That means mod alpha equal to n plus 1. This is m comes out. Summation r1 by r to the power mod alpha equal to n plus 1. Clear? And this is finite. As n tends to infinity, why it should go to 0? Why? If I made a mistake somewhere? Because this is a, as n tends to infinity, this. Okay. Okay. Just a minute. Can you see why? Huh?
I think r1 by r is less than 1.
But why it goes to 0? Hmm? It is finite, I can say, but why it goes to 0?
n plus 1 factorial tends to 0. N infinity.
No, that gets cancelled. No, mod alpha is n plus 1. This gets cancelled. No, somehow 1 by n should be there. I made a mistake somewhere. But let me check again. Let me check. Let me check. You understand what is? There is a mistake I have done. Why this goes to 0? Huh?
Like sir, alpha will not get cancelled. Like alpha is the mod of alpha factorial is there. We cannot
No,
take
because
it.
mod alpha, see mod alpha factorial. So here I am taking the summation on mod alpha equal to n plus 1, right?
Yes, sir, but that's changing. So we cannot take it outside and cancel it from n plus 1 factorial.
No. Mod alpha is n plus 1. So I can write mod alpha here n plus 1 factorial. Yes or no?
Oh, yes.
Right. So this gets cancelled.
Sir, if mod alpha is not changing, it is equal to, then why we are taking summation, sir? We can directly put.
What? Yeah. This I can write. This I can write m summation n equal to 0 to infinity r1 by r to the power n plus 1. This I can write. Okay. Because again I can write substitute mod alpha equal to n plus 1. Yes or no?
Yes.
Just a minute. Hello? 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 हाँ ठीक है, आप आइए, घर में आइए, मैं ऑफिस में काम कर रहा हूँ अभी, मीटिंग बाद में फोन कीजिए. हाँ, हेलो. Why this summation goes to 0 as n tends to infinity? Why?
Now we can take like r1 by r raised to power and outside and like.
Okay. That is the sum. X to the power n, right? 1 minus 1 minus. This is what is the sum? What is the first we have to take? Just a minute. Okay. Why this goes to 0? Huh? Anyway, I have to check this. I also thought that this 1 by for n plus 1 factorial it gets cancelled, but it is not. I have to show that this goes to 0. This goes to 0 as n tends to infinity.
Sir, here mod
Like this
alpha is
summation.
constant.
Huh.
Here mod alpha is constant. So just as you took mod alpha factorial outside, we can take this to be r1 over r upon n plus 1. Sorry, raised to n plus 1.
Yes. Then, but still, yes. So this will be nothing but, yes, this will be
It
nothing
will be
but
a raised to the power n, where a is less than 1, so it will go to 0.
exactly. This will be equal to r1 to the power r to the power n plus 1. Exactly, right?
Yes, sir.
Yes. And this goes to 0 as n tends to infinity, because a to the power n goes to 0 as n tends to infinity and a is less than 1. Clear? Is that clear? Yes or no? Yes, good. So this goes to 0. Thank you. Sorry, I also thought that because of that. Okay, anyway, thank you. So these imply fx is summation alpha d alpha f of x naught by alpha factorial x minus x naught to the power alpha. So because from here, so this goes to 0, the remainder term. So you can write for any alpha. Okay. So this proves the theorem. This proves the theorem. Okay. Okay. Thank you. So this is a very interesting theorem that when you can say if and only if the f is a real analytic function. Okay. Today we stop here, and next class we will be doing the. Now we will see how I use this theorem for a OD and PD. Okay, to show any PD or OD has a real analytic solutions. Okay, this is called Cauchy-Kovalevsky theorem. It's a very important theorem, Cauchy-Kovalevsky theorem. Okay, next class we will do that. Okay, anything you want to ask me? Okay then, thank you. Thank you.
Thank you, sir.